a little bit of chapter 10, starting with Tyler. Number 1, you've got graphs of force, of magnitude of force versus the magnitude of the greatest first. They're all the same. They all have an area of 12, so they're all the same. Number 2. Okay. And I think Wes kind of had this question earlier. All right, first of all, the picture is on the other page, the next page over. It's just a ball bouncing off a surface, and the angle is in the middle there. Okay, so that figure shows an overhead view of a golf ball bouncing off a tree trunk with no change in its speed. During the collision, the force F on the ball by the trunk causes a change in momentum in the linear momentum of the ball. If the angle is increased, and assuming that the duration of the collision is unchanged, do the following: increase, decrease, or remain the same. So let's quickly sketch it. Okay, so that's our original, and then the angle is increased, so this is going to be sort of more spread out. And more like that. Okay, so we're hitting the tree, bouncing off that way, and magically the speed does not change. So first question, does the change in x momentum change? Or does the change in x momentum change? Does it increase, decrease, or stay the same? So real quick, you know your x is this way. What originally was change in x? Final minus initial? 0, because this chunk is the same as this chunk. Final minus initial is 0. Now we have a much bigger x component over here, but what would you say the change in x is? Right, so the change in also 0, good. Okay, so that's the same, that's still just 0. What about change in y? Now, a little careful here, because these are opposite directions. So if you're doing final, which is like that, minus initial, so minus that would be plus that. So good, it doubles. Just kind of compare what that would be versus these components. There is some change in y, of course, but is it less? Yeah, obviously less, because if you did final minus this initial, that's not going to be as tall as that. All right, how about the magnitude of momentum overall? So, like this one, okay, here's our final. Minus initial. So take the reverse direction of that. But what should that? Yeah, it should be the same answer anyway. So also less, good. Okay, now how does this relate to f of x and f of y and then f overall? What do we know about how change in momentum is related to force?
Change in momentum is integral with force.
Good, force and time. I'm going to call it average. You could also say that. And it said the time, it said something about the time, I think. Okay, yeah, assuming the duration of the collision is unchanged. So t would be a factor here, but it's saying it's not.
Okay.
So in that case,
It would have to be less.
yeah, all of your answers would just correspond here. So that would be unchanged, it'd be 0, less, less. Okay. One more? One more. Number 3 looks short. Number 3 is going to Connor, back to you. It's short, promise. And then we'll stop. All right, so number 3, you have this table on the next page. It says the following table gives, for 3 situations, the masses in kilograms, velocities in meters per second for the 2 particles in figure 10.9, whatever that is, for which the center of mass, for which is the center of mass of the 2 particle system stationary. So you simply just have 2 particles moving. It tells you their mass and velocities, in which case would the center mass be stationary? Very good. Because your momentum, your net momentum there would be nothing. All right. Perfect timing. Thank you, Connor. Okay, number 5. All right, so it says 2 bodies undergo an elastic one-dimensional collision along an x-axis. The figure below is a graph of position versus time for those bodies and for their center of mass. So I actually want to do B and C first. Which line segment corresponds to the center of mass before and after the collision? Now realizing that the center of mass, like the velocity of center of mass, that should not change, assuming there's no, external forces. Exactly, good. So 2 and 5 must be the center of mass velocity. 2 before and then 5 afterwards. Okay, so then back to A. Were both bodies initially moving or was one stationary?
One is stationary.
Yeah, one is stationary. It is staying at the same x value, so it's not moving. Okay, then to D. Is the mass of the body that was moving faster before the collision greater than, less than, or equal to that of the other body? So how do the mass of 1 and 3 compare? In which, assuming they do collide, like what does line segment 3 turn into? Yeah, it goes to 6. And then what does 1 turn into? 4. Assuming, of course, they collide. Otherwise, 1 and 6, it never hit. It just continues staying still. So if one of them was much more massive, would you expect a big deflection or a small deflection if one's really massive? A small. So how do those deflections compare?
They must be the same.
Exactly. They must be the same mass. Because a deflection like that angle between 4 and 5 or the angle between 5 and 6 is the same angle. So they must have the same mass. All right, now let's compare that to number 6. Slightly different graph. Brandon, this one's going to you. So it says one body catches up with a second body, and they undergo a one-dimensional collision. Graph below shows position versus time of these bodies and their center of mass. So I'd also still like to do B and C first. Which must be the center of mass line segment before and after the collision, Brandon?
2 and 5.
Yeah, still 2 and 5, because the velocity of center mass shouldn't change. That slope doesn't change. A, which one is the faster body before the collision?
3.
3, how do you know?
Bigger slope.
Steeper slope? Yeah, so 3's got more slope, steeper slope, so it's definitely moving faster. Which one, and again, you'd have to assume they actually do collide here, but which one, the initially faster body after the collision, so what does 3 turn into? 6, and then 1 must turn into 4. So here is the mass of the initially faster body. So is the mass of 3 greater than, less than, or equal to that of number 1? How do you know?
There's a bigger angle between the center of mass and...
Very good. It must be pretty light, because it had a big deflection. Like 1 to 4, that barely got deflected at all. But 6 must have been the lighter one. Very good. Okay. Moving along. Number 7, Zach. It says, the figure above there shows 4 situations where 3 identical blocks undergo an elastic collision on a frictionless surface. In situations 1 and 2, 2 of the blocks are glued together, I guess before and after. The initially moving blocks have the same velocity, so they all, whether it's 1 or 2 blocks, start with velocity v. Rank the situations according to their total linear momentum of the blocks after the collision. But we know that the total linear momentum after the collision would equal what? If momentum is conserved. The momentum we have at the end must equal the momentum from the beginning. So even though it says the total linear momentum of the blocks after, it doesn't really show you those velocities, but it doesn't matter because it's going to be the same as what it was before anyway. So which ones have the bigger or more momentum initially? 1 does, and 4. Even though 4 separate blocks, it's still 2 masses, same velocity. All right, so 1 and 4, then 3 and 2. And then the speed of the rightmost block after the collision. Yeah. Which one's going to end up good? Very 1, because you have double the mass, and that's just hitting 1 little block.
Yeah.
So good. 1's definitely going to be the fastest.
4 and 2, 3. 1, 4, 2, 3.
Nope. 4 is next, but it's tied with another one.
1, 4 are the same as 1. I mean,
No.
4 and 3 are the same.
Yes, 4 and 3 are the same. And honestly, in number 4, would that blue block ever even hit the purple block? No. If they have the same, well, I shouldn't say that. It will, yeah, it will hit, but after it's hit the rightmost block anyway. Does that make sense?
Yeah.
Okay.
The middle block's going to hit the right one first.
Right. Okay, so 4 actually ties 3, because they would both end up with just speed v. And then 2 would be the slowest. Okay? 4 ties 3. Because they would, the rightmost block would both end up with velocity v. Eventually, by the time the rightmost block was hit. All right, 9. All right, so not bad. Daniel. All right, we got 2 blocks, A and B. They have linear momenta with directions as shown, with magnitudes 9 and 4. So A is going to the right at 9, B is going to the left at 4. What is the direction of motion of the center of mass of the 2-block system over the frictionless floor?
To the right.
To the right, because we have more momentum to the right. If the blocks stick together during their collision, in what direction will they move?
To the right.
To the right, because we have to conserve overall momentum to the right. C, if instead block A ends up moving to the left, will the magnitude of its momentum then be smaller than, more than, or the same as block B?
Smaller.
Yeah, it would be smaller, because B would have to be much bigger to keep the overall to the right. All right, one more, 11. Wes. Body Q with linear momentum 2I minus 3J collides with and also sticks to body R with linear momentum 8I plus 3J. In what direction do the bodies move after the collision? Exactly, just to the right, because the J cancels out. Okay, good, not too bad. That gives us 18 minutes to do our lab, which is fine.